We've begun to talk about antiderivatives, and in particular, we've been finding general antiderivatives, which we also call the indefinite integral. And when you find those, we always put a plus c constant at the end, because the general antiderivative is a family of functions that differ by a constant. In other words, the y-intercept just changes. That function is, or that group of functions looks the same, but it's shifted vertically in the plane. So what we can do, if we know one point on the curve, we can actually solve for c. And that's what we're going to do when we solve an initial value problem. You can see here in this example that we're given a derivative function, dy over dx equals 10 minus x, but we're also told that y of 0 is negative 1. And what that really means is that our actual function y goes through the point 0, 1, or excuse me, 0, negative 1. So when x equals 0, y equals negative 1. So the way you solve these problems is you go ahead and find that general antiderivative, or the indefinite integral. In our case, the original function is y equals 10x, that's the antiderivative of 10, minus x squared over 2, which is the antiderivative of x, plus some constant c. Right now we don't know what c is, but remember, we do know values for x and y in this curve. So we simply do substitution to solve for c. I'll put negative 1 here, equals 10 times 0 minus 0 squared over 2 plus c. And you do a little math there with 0 and you find out c equals negative 1. So we've found the value of c. To solve the initial value problem, we want to give the original function. So our final answer is going to look like this. It's the quadratic negative 1/2 x squared. That's the same as negative x squared over 2, plus 10x. And then instead of plus c, I write minus 1 at the end. And this is the solution to the initial value problem. The curve that we were looking for is y equals negative 1/2 x squared plus 10x minus 1. It's really all there is to these problems. Simply we're doing the antiderivative and then plugging in x and y to solve for c. Let's take a look at another one. In this second example, you can see we have a derivative which is dy over dx equals 1 over 2 squared of x. That is a famous derivative that you have memorized, so finding the original function should be a piece of cake. The initial condition is y of 4 equals 0. Remember, that tells us that when x is 4, y is 0 on the curve. Now the reason I said this derivative is one you should have memorized is this is the derivative of the square root of x. So that means the original function must be y equals the square root of x plus some c. We won't know what c is until we plug in the initial conditions. So when x is 4, y is 0, so 0 equals the square root of 4 plus c. And when you solve that, I think you'll agree that c equals negative 2. And then we're going to write our solution with the entire curve. So we're going to write y equals the square root of x minus 2. That's our solution curve for this initial value problem. Okay, now this process even works when you're given the second derivative, as long as you're given an initial condition for the first derivative and an initial condition for the original function. And that's what I'm going to show you on this last example. So here you can see we are given an initial condition for the first derivative, which is 0, 2, and an initial condition for the actual function, which is 0, 0. Okay, so we're going to work our way backwards twice in this process. to find the first derivative, which is just dy over dx, we do the antiderivative of the second derivative. The antiderivative of 0 is some constant. We don't know what it is, but we know it was a constant. Because we have an initial condition, we can solve for the constant. In this function, when x is 0, c equals 2. Well, there's nowhere to plug the 0 in, so that just tells me that c equals 2 here. The constant is 2. It doesn't matter what the x value is. So now the derivative is really just 2. To go back to the original function y now, we have to do the antiderivative of 2. And the antiderivative of 2, as you know, is 2x. And then this is a general antiderivative, so we put the plus c on the end. Now we'll use this initial condition, 0, 0, to solve for c. And I think you'll see pretty quickly that c in this case is going to be 0. And so what we know now is the solution to the original differential equation. This is called a differential equation. We're not going to use that terminology for a while, but the solution to the initial value problem, where the second derivative is 0 with these conditions, is y equals 2x. Now, after you practice some of these, you're going to have a few problems where you do some applications. So remember, if we talk about position, velocity, and acceleration, those are really just derivatives, right? Velocity is the derivative of position. So if I give you the velocity and an initial condition, you can work backwards like we have here to find the position function. If I give you the acceleration and two initial conditions, one for the velocity and one for the position, you can work your way back twice like we have here to get the original position function. So keep that in mind. Don't panic when you see some applications where there are words involved. You use the same process. That's how we do the initial value problems. We use these antiderivatives to solve for the letter C. Good luck on these problems.